easy to overthink what you're being asked here. So first of all, what do we mean by irrational number? Okay, well, give me some examples of irrational numbers. All right, square root of 2, pi, no, not that one, e, square root of 3, we can do square root of 2 plus square root of 3. I mean, any square root of an odd number any root of 2 is irrational. 17th root of 2 is irrational. You can do, square root of 2 plus 1, something like that. Those are all irrational. So we're thinking about two different irrational numbers, so their sum is rational, right? Anybody? Yeah. Say it again.
So ln of 6 divided by ln of 3 plus ln of 1.5 divided by ln of 3 equals 2.
That whole thing equals 2?
Yep.
And how do you know that ln of 6 over ln of 3 is irrational?
I played around with it on my calculator.
And what'd you get?
Don't know how big that number is.
Yeah, but I mean, like, it's probably is irrational, but because I mean, if you do the math, you get ln of 3 here, so it's ln of 6 plus ln of 1.5, right? So this becomes, you can use this 6 times 1.5, right? By the properties of logs. And what is 6 times 1.5? 9, so this is ln of 9 over ln of 3, right? Yeah, so it's 2, because you can always think that 9 is 3 squared, so it's 2 ln of 3 over ln of 3, so those cancel, so you do get 2. Right. Sure. I mean, I'm just not 100% certain that ln of 6 over ln of 3 is irrational. Well, ln of 3 equals some number, right? This means that 3 equals e to that number, right? So, I mean, is x irrational? I mean, I know our calculator is going to show a random decimal thing, but what if it repeats every 1,000 decimals? But I mean, I'm pretty sure this works. It's a little, well, it's good. I like that. I mean, how did you come up with that? Yeah. Well, I guess that works. There's the infinitely many very simple cases. How about 1 plus square root of 2 and 1 minus square root of 2? These two are irrational numbers, right? 1 plus root 2 is irrational. 1 minus root 2 is irrational. You add them together, what do you get? 2. Right? So, so you can do infinitely many examples like that. 3 plus pi, 7 minus pi. Add them together, you get 10. Right, so any combination like that, it will still be irrational. And this is what I mean here, you can do just whatever. So that works. I mean, for the b, we can do something like that. And you can do 3 plus square root of 2 and 4 plus square root of 2. You subtract them, the square roots of 2's cancel. Okay, this is should be the product is
So it would be 2 and then the square root of 2 is cancelled.
yeah. Now, how about C?
Square root of 2 times the square root of 3, because we can understand that as 2 to the 1 half times 3 to the 1 half.
No, because on the same base.
So I chose some reciprocals, but pi times 1/5.
So you considered pi as one irrational number and 1 over pi is another irrational number. Yeah, that works.
Isn't 1 over pi actually expressed as a fraction?
Well, it's pi to the negative first power, right? What did you come up with?
I got square root of 2 plus the square root of 8 times the square root of 16.
Okay, that works. One thing that we should know about the products is that there is such thing as there's a thing that we call conjugates, and you probably have seen it in college algebra when you were rationalizing the denominators. And the conjugates are basically your difference of squares formula. We usually call these two items that are basically identical but only differ by sign in the middle, we call them conjugates. And we know the products of this, right? What is the product of a minus b and a plus b? A squared minus b squared, right? So a lot of those products can be done like that. If you take square root of 2, let's say minus 1, and you multiply it by the conjugate, right? That also works because you will get rid of the square root. And this is how you rationalize denominators.
So that works for C also.
Yeah, that works for C also. So that equals 1, right? But this is, yeah, so you've used that in college algebra. When you had to rationalize denominators, you did that conjugate trick. But all those other examples are also valid. Root 2 times root 8 works, and so forth. You can do root 8 divided by root 2. That also works, right? For D, you will say, if I do square root of 8 divided by square root of 2, that is, 2 root 2 over root 2, which is 2. So there are many of those examples. But I really like that natural log mass. This is cute. Just only if we can prove it.
Is that to the square root of R?
What was that?
Is that the square root of R?
No, that's the square root of 2 already crossed out.
Oh, okay.
These are the square roots of 2's canceled.
Square root of 8 expressed as
Right? Because when we think of square, these notes are really messy. When you think of square root of 8, you can always think of this as square root of 4 times 2. And you can take square root of 4, which is 2. So we can always do that with composite numbers. If you have a number that can be expressed as a product of a perfect square and something else, you can always do that. Like, let's say square root of 75. 75 is 25 times 3. So you can take square root of 25, so that's 5 square roots of 3. Right? This is a mess. Okay. Other questions?
You also have question 1. Yeah.
Oh yeah, this one is cute. I don't remember how I did that.
Not that one. The other one.
Oh, the other 4? This 4?
Yeah. No.
both fours.
Both 4s.
Yeah, maybe that was one. Yeah, both.
Both 4s? Well, let's do the algebra 4 first. I don't remember how to do the other 4. Okay, well, there's probably, yeah, that one is nasty.
It ends, and I set it up to equal 0 at the end, and I just didn't go any further
Uh,
Just
All
kept
three
it
of their
all
problems
factored.
were so nice, and then they got
yeah, this one contains. Looks like there is a misprint here. Yes, that should be a cube. Uh, well, let's do it with a cube. It'll be a lot easier. Because with the cube, it factors nicely. Because then it's if you factor everything, it's x plus 2 plus 1 over, you can pull out an x minus 2, right? And on the last one, you pull out an x, that's x squared minus 4. And then x squared minus 4 using the difference of squares formula becomes x plus 2x minus 2. So if I factor it further, right, this is a lot better if that was a cube. Otherwise, it's a mess. Because this gives me the least common denominator, right? What is the least common denominator? Right, you need all the factors, right? Just like we did in the LCM. You need all distinct primes with to the highest power. So the best thing that you can do is to multiply both sides of this equation by the least common denominator, right? That's the big trick we learned we did that in 099 even, just doing that. So what happens on the right? Yeah, just everything just cancels, and you're left with 8. Now here you have to be careful. We're going to take this entire expression and distribute. Right? We're going to use the distributive property. So when you multiply this LCD by the first fraction, what's going to cancel? X plus 2 will cancel. And what's left? X, right, x minus 2. And when you do the second product, x's cancel, x minus 2 cancel, and you're left with x plus 2. So plus x plus 2. So yes, you distribute, but that becomes a quadratic, basically, right? It's x squared minus 2x plus x plus 2 minus 8 equals 0. Made it so much better if you just change one little power. Otherwise, it's a mess. So let's see. I think it's even factors nicely. X squared minus x minus 6 equals 0. Look at that. That's factorable, right? How would we factor this? We lost a student, didn't we? Was there another? We had 8. Now we have 7. There's somebody else here, right? You ended up registering, right? So yeah, so right now we have only 7 on the roster. They're not going to make us. We're good.
How did you get that -6?
2 minus 8. So factor, right? What is it? X minus 3, x plus 2 equals 0. That's a 0. So you set each factor to 0. So x minus 3 equals 0. Or x plus 2 equals 0. So x is 3. X negative 2. Are we done? You have to kind of check them. You don't have to like check them, but what should you check? Right, doesn't make zeros in the denominator because while solving this problem, we completely killed the denominators, right? So we solved this problem with complete disregard for the denominators. Well, one of the answers is x equals negative 2. Can it work? Can x equals negative 2 work? Because you go in here, you plug negative 2, you get 0 in the denominator. So x negative 2 should not be a solution, right? So this is the only way you check it. You don't have to, I mean, you can if you want to, but clearly when you plug negative 2, you get division by 0. That doesn't work, right? So the only answer is x equals 3. That one does not turn any denominators into 0. This is, we can call it extraneous solution. So good. Oh yeah, a lot cleaner. It's just, otherwise it's a mess. This is very clean. Sorry about that. This is the only assignment you get typed by me. The rest of them going to be proofread millions and millions of times. Now, the other 4? How did I do it last year? It was a cute way of doing that. It took me a while. I need to think. Why does it say 1 all of a sudden?
Start over.
Oh, it's, yeah. So numerical examples are not acceptable. Make a general argument. Does anybody come close?
I said that because A is less than B, A over B is always going to be the fraction less than 1. But B over A gets infinitely bigger. Could be bigger because you could pick numbers that make it B over A being like super large. But A over B is still going to be 0. So A over B is always going to be.
Well, but you see, the thing is always.
Yeah.
So you can always pick something closer, maybe. I get your argument that, most of the time that might work, but you want to be.
That's all I got.
Really? No, there's got to be more precision.
Because if you can use, if B is bigger than A, then it's always going to be over 1. It's always, but that fraction will always be larger than 1.
Yeah, but the other one is less than 1. But which one is closer to 1? That's the question. No, there's 1 always going to be close to 1. Okay? So that's the question. Like, clearly A over B is less than 1. B over A is bigger than 1. But 1 is always going to be closer to 1. And again, it feels like it should be A over B, because what you're saying is you make B large enough, you can get B over A to be 1,000.
Well, could you say that because B over A isn't always going to be smaller, closer, that A over B has to always be closer?
Well, this is the thing that you can kind of start with, because the answer should be A over B, right? Because A over B is always between 0 and 1, right? No matter how hard you try, if both are positive, if A is less than B, then the ratio is less than 1, but still be positive, right? So it's a very small range for A over B. While B over A is clearly bigger than 1, but it's could be as large as you want. That's what she was saying. So it feels like, the answer is this. But why is it always the case? Because, what if I make them, very close together? You know what I mean? So, but yeah, the answer should be able, because B over A, you can just do a numerical example here and say, okay, B over A will not, A over B will not, no, B over A is not the closest one, okay? Now, I think this is how I did that argument. So, let's talk about this. So yeah, the answer should be A over B, but we have to make a good argument. And I get your argument saying that, B over A will lose, but will it always lose? That's the thing, right? Well, how do you know, how can you measure what's closer to 1? Well, let's do a numerical example, okay? At least we get a taste for it. Give me some values. Give me a value for A, and give me a value for B, and then we'll play. 5 and 75? All right, let's do 5 and 75. Okay. That's fine, all right? So what is A over B? So it's 5 over 75, which is 1/25th, right? And what is B over A? 75 over 5, which is 25. Which one is closer to 1? A over B. But how much close? What is the distance from? But I mean, how close is A over B to 1 right now? Can you tell me? What? Well, not ways away, but you can actually. Yeah, you just say, well, how close is this number to 1? So what is the distance? Oh, yeah, 15. Sorry. Not 25. But anyways. But yes. Right, you just say, well, how close is this to 1? So you have to actually subtract this number from 1. Okay, so this is the distance from this number to 1. What is the distance from this number to 1? So you go 15 minus 1, so it's 14, right? So this is the distance from 1, this is the distance from 1. Well, which one is smaller? 14/50, right? So we can do kind of the same thing. We actually say, well, in general argument, how close is A over B to 1? And the answer is, well, it's 1 minus A over B. This is how close A over B to 1, right? And I can say, well, how close is B over A to 1? Well, it's B over A minus 1. Right, like we did before, numerically. So now we literally have to compare which one of these numbers is bigger or smaller, right? Now, how would we do that? Not really. I mean, we still, in terms of variables, oh, yeah, sorry. So do the common denominator, right? I mean, actually do the math. So B over B, so it's B over A over B, right? And here you have B over A over A. B minus A over A, right? Same numerator, different denominators. So which fraction is smaller? The one that have a bigger denominator or the smaller denominator? Right? So the fraction that has, if you have two fractions, same numerator, different denominators. For example, 3/7 and 3/11. Which one is smaller? 3/11. The one that has the largest denominator is smaller. So which number is bigger, B or A? B, right? Since B is greater than A, we know that B minus A over B is less than B minus A over A. So therefore, A over B is always closer. That's how we did it last year. So we literally looked at the distance, and then you have to analyze it generally, which one is smaller. And we just got lucky that numerators came out the same, then you just compare denominators. And since B is greater than A, so it's always going to work like that. Oh, that's cute. Again, I'm just massaging your mathematical brains with that. It's, you won't see anything like this on the test. You might, after we actually get into the textbook, you'll think back of our week 1 with feeling of nostalgia of sorts. Yeah, that's really what it is. You don't need to know any math whatsoever. You just need to know simple arithmetic to answer this question, right? You just need to understand. No, you need to know fractions. Like the largest denominator. If the denominator is the same, will give you a smaller fraction and so forth. Okay. Anybody did the extra credit? No. I don't remember how that works. Okay, well, let's start learning. By the way, we're still kind of, I'm going to review a little more today and maybe Friday. We're just going to get through some basic theory of functions, kind of college algebraic review, function notation, odd even functions, and so forth. So, oh, this is calculator notes, sorry. Okay, here we go. So we function review. So what is a function? If I tell you, give me a definition of a function. Sure. There's no repetition in the x, right? One input has one output.
Like if you were to graph them, you would not have two different y-intercepts. Or x-intercepts.
No, you're right, y-intercepts. Or any 2 points that are above each other. So that's your vertical line test, right? What were you saying? I'm sorry? Yeah, passive vertical line test. But the way we start talking about functions, we usually first define a notion of a relation, which is just a set of ordered pairs. Just tells you that one number relates to the other number by whatever means. You don't need to have numbers. I can have students, whatever. You're all in the same classroom, so there's a relationship. I can write all your names as the x coordinate and math 166 as a y coordinate. So this is our relation. So every relation is a function, not every function is a relation. There's a very specific thing, but as far as we're concerned, an example of a relation, all I need is just, a bunch of ordered pairs. These are the ones I have in my notes. So is this a relation? Yes. It's just a set of ordered pairs. Is this a function from what we just kind of talked about? No. Why not? Because it has these 2 points, right? One relates to 1 and one relates to 3 at the same time, which is okay for a relation, but it's not okay for a function. We want to have an x produces a unique output. Okay? So this is what you were saying about y-intercepts or the vertical line test. If I actually plot this relation, it has only 4 points, so 1, 1, negative 1, 2, 1, 3. Well, my scale is way off. And 2, 5, something like that, right? So this is what we mean by the vertical line. So it kind of breaks down here. So it's not a function. But I can still talk about the domain and the range of this relation, just like we'll be talking about domain and the range of functions. So what is the domain in general? When I say, find the domain of this, what am I looking for?
A set of x values that are true for a function.
Well, right. Well, for this case, it will be just the very simple set, negative 1, 1, and 2. So just 3 points. But in general, we just look for the x values used in that function. So sometimes it's all real numbers, sometimes it's limited. But in this case, the domain is just those points. So negative 1, 1, and 2. So this is using the set notation, right? Just list of values. There's nothing in between. We just use those 3 points to produce that relation. The range is slightly bigger. These are all y values. 1, 2, 3, 5. Right? Yeah, I wouldn't be sitting underneath that every day. Yeah, something will happen. So is that okay? You kind of remember that? If I give you a graph of a relation, let's consider something like this. I'll give you what is this? Well, if I try to graph that relation, what will I get? No. X squared plus y squared of sorts equals some other number that's positive. What does it give me? Circle. It's a circle centered at 1, 0, so this is the center of the circle. What is the radius of that circle? 2. Right? Remember the general equation of the circle, x minus h squared plus y minus k squared equals r squared, where hk is the center, and r is the radius. So this is the circle of radius 2, right? So we'll do this, radius 2. So 1, 2, 1, 2, so close enough, right? Well, I'm just looking, what is the value of h? So that's 1. And what is the value of k? 0. Well, what is subtracted from y right now here? Yeah, that's a y squared. Oh, no, that's a y squared. Yeah. So the center then, it's 1, 0. So is this a function? No. Fails the vertical line-test, all that good stuff. But what is the domain of this relation? From -1, 3. Including -1? Including 3? So one way to write that using the interval notation, using the brackets, we use brackets for inclusion and so forth. Another way to write it, if you recall your set builder notation, you can say the set contains x's such that what? Each x is between -1 and 3. You don't even have to use x. You can use any letter. Let's just use another letter so we don't get, I can say, I don't know, p's, full of p's, that hp is between -1 and 3. So that's a set builder notation. Doesn't matter what you use for variable, it will still produce numbers from -1 to 3, including -1, including 3. How about the range? What is the range of this relation? -2 to 2, because the radius is 2, so this point right here is 1, -2. This point right there is 1, +2. So on the y, we just covered everything from -2 to 2, including -2, including +2. Those are brackets. Is that okay? Or again, using the set builder notation, full of p's, such that each p between -2 and +2. Set builder notation. So basically, this is how you read that. So this set contains a bunch of elements, whatever. So what do all those whatevers have in common? Well, every whatever is between -1 and 3, including -1 and including 3. We read that vertical bar as such that. So it builds a set. Because I cannot list all the elements, clearly, right? Because it's a continuous, infinite set. So there's interval notation or set builder notation. And you'll be seeing both throughout the book, so don't freak out when you see that. Sometimes, if I want to say, for example, so here are some examples of set builder notation. Let's say I want to just list all real numbers from, again, -1. Well, I just say all real numbers greater than -1 and less than or equal to 5. So then all I have to do is just to say, well, what all those p's have in common? They all have to be greater than -1, right? So I'll write it like that. Each p is greater than -1, but less than or equal to 5, so I'll toss that in there. The equal inequality, right? But let's say if I said all integers, or let's do all rationals, that's better. All rational numbers from -1 to 5. Okay? Because right now my set includes all real numbers from -1 to 5, including all the irrational. So one addition to the notation you can say is that, well, it's all p's that are members of the rational set that satisfy that condition. So that's another way to write that. Anyways, don't, you'll be all right with that. It's not that big of a deal. You'll see it in the book, and it'll come up. Okay. So we understand. Now, like if I give you this, determine whether the relation is a function. Without, let's say, graphing. If I, for example, give you this, like we know it's a circle and all that good stuff, so it shouldn't be a function. But how would you do this algebraically? So what you're going to try to do is to solve for y algebraically and see what you get. So if you try to solve this for y, how would you go about that? Right, subtract x squared, so you get y squared equals 1 minus x squared. Take the square root. What do you need to remember when you take the square root like that? Right, plus or minus. So the right away you see for every x that you plug in, you're going to get positive and negative result. Okay? And actually if you graph these two functions, the positive square root produces this graph. So it's a function of an upper semicircle. And if you graph a negative square root, it's a function of a bottom semicircle. So you still get your circle as defined as two functions separately. Well, it's not a function as a whole. Right. The
Domain restrictions on that?
yeah, but greater than 1 is already outside the domain, right? I mean, you can just say consider positive y, so you just have an upper semicircle, you just play with that. And you'll do that in calc too, let's say, you just mess with half of it. But algebraically speaking, you just get, plug in 2 in there, you get plus or minus 1, so that doesn't work. Okay? At the same time, if I put if I put cubes in there, x squared plus y cubed equals 1.
So that top one, the answer, like, we're trying to determine if it's a function.
Right, so the answer is no. Because for every x, you'll get 2 different y's. Well, except for like 1 or -1. So if you follow the same thing, you try to solve for y, you'll get y cubed equals 1 minus x squared. Right? But then if you take a cube root, you no longer need a plus or minus because the cube preserves the sign. So there's no plus or minus. You get a nice, pretty answer. For every x you put in there, you get 1y. So that's going to work. There's no conflicting results like that. So yes, a function. All right, so function notation, going kind of fast through that. We've seen function notation all over college algebra. So this is your f of x thing, right? F is the name of the function. X is the independent variable. And f of x is your dependent variable. That's the value of the function at any given point in the domain. So for example, f of x equals negative x squared plus 3x plus 4. Okay? I mean, you've dealt with it before, so if I ask you something like this, what is f of 2? Are you going to have any issues? You all understand what you're being asked to do? What are you asked to do? So we'll just substitute 2 for x, right? Now, so what does that come out to be? So here's the question. Is this going to remain negative or not? Yeah, it will remain negative. Because this negative sign is not, I mean, the square is not squaring the negative. It's only squares the x. So this will remain as negative 4 plus 6 plus 4. 6. Okay, so this is the big thing. If we had parentheses like that, then it would make it positive. But we don't. So this is equivalent to saying negative 1 times 2 squared. So that remains a negative. Okay? Good. How about f of negative 1? We'll do it the same way. So it's negative of negative 1 squared. So in this case, kind of kills the negative, but then there's a negative up front anyways. Plus 3 times negative 1 plus 4. So that's minus 1 minus 3 plus 4. Oh, we'll get 0. Right? What if I ask you f of t? What is f of t? Yeah, negative t squared plus 3t plus 4. Right? Whatever goes in a little parenthesis replaces the x. So if I ask you that, f of smiley face. So there will be negative, about to put a smiley face in there, plus 3 times, about to put a smiley face in there, plus 4. So that's what that is. It's a lot of smiley faces. But that's the idea. Whatever goes in the little parentheses replaces the x. Is that okay? So well, then it will just be the same as f of 2, right? But I can have f of, let's say, 2x like that. So then again, you just put 2x for every x. So this is negative 2x squared plus 3 times 2x plus 4. And then I can simplify that. This is negative 4x squared plus 6x plus 4. So if I put that kind of a thing on the inside, I multiplied every variable by 2. If I put this on the outside, then I'm multiplying the entire function by 2. So this is 2 times negative x squared plus 3x plus 4. Right, 2 times the function. So simplifying this gives you that. So not the same as, so you see there's a difference between putting 2 on the inside and putting 2 on the outside. Putting 2 on the inside, you mess with the independent variable. Putting 2 on the outside, you mess with the dependent variable. We'll actually get to that, but we'll see how what this will do. It will make, because I mean the graph, first of all, the graph of this function is a parabola. It's a quadratic. It's actually going to be an upside down parabola because of the negative in front of the square. So it's some kind of an upside down parabola. What 2 on the inside will do, it will actually make that parabola skinnier like that. Yeah, it's not really sloped. So this is messes with the x, it will either shrink or stretch it like that. The other one will actually stretch it or shrink it vertically. So with parabolas, it almost looks the same. Whether you compress it like this or stretch it like that, you still get kind of a fatter parabola. But when we're going to get in our squigglies in this class, because we're going to see a lot of that, it will be different between compressing like this, so it will increase the frequency, or stretching like that, so it will increase what we call an amplitude. So it's very important. I mean, we'll review those transformations on Friday, actually. Okay. But yeah. But I can also do something like this. How about f of x plus 2? How would we do that? Again, that's your smiley face. X plus 2 is the smiley face. Wherever you put a little parenthesis replaces the variable. So you put x plus 2 for every x. Right? Same pattern. So it will become negative x plus 2 squared plus 3 times x plus 2 plus 4. Slow down there. It's not just x squared plus 4. You have to be very careful when we square those. Right, it's x squared plus 4x plus 4. So we should be, and I've mentioned this before, we should be very comfortable with these formulas for squaring a sum or difference. If it's a plus, it's a plus. If it's a minus, it's a minus. Or if you know, like in 099, I drove you guys crazy with those formulas, right? Remember that, Elizabeth? We spent goods, I mean, a whole semester I was just tossing it to them so they'll get it down, right? Remember that? When in doubt, just FOIL. X plus 2 times x plus 2. FOIL that. But x squared plus 4 will just be very wrong. Right? So if I keep simplifying this, negative x squared minus 4x minus 4 plus 3x plus 6 plus 4. So 4's cancel. So what do we end up with? Negative x squared minus x plus 6. We'll actually end up with the same shape, just shifted 2 units to the left. That's what this will do. It will shift the graph to the left. We'll talk about this again later. Is that okay? All right, so that's how function notation works. Basically, keep reminding yourself about that smiley face. Whatever goes in the little parentheses replaces your variable, regardless of what it is. Could be, I can put another function in there, right? It'll just replace every x. Yeah, it's just from them, whatever. Right, because we, as far as making up the x values, are there any restrictions on the x? Are there any x's I need to avoid? I mean, I can put any x in there, right? So this is the domain. Domain of this function would be all real numbers, right? Regardless of what x is, I can plug it in and I can get a real number, okay? That's the key. So when you talk about the domain, you're looking for the x values such that if you plug them into your function, the function spits out a real number. For us, that means no division by 0, right? No square roots of negative numbers, because those produce something that's not exactly real. Well, no natural logs of negative numbers. I mean, no logs of negative numbers or 0. Those are undefined, right? But for now, we kind of, well, let's try that. Find a domain. So I'll give you a function, f of x equals the square root of 4 minus 3x. Okay? So you see a square root. So that should trigger an alarm. That, okay, there could be something wrong. So when you're dealing with a function that has a square root, or any even root for that matter, doesn't have to be square root, it could be the 12th root, we need to make sure that we do not take square roots of negative numbers, right? So that means the radicand, this is what we call a radicand, 4 minus 3x, has to be non-negative, right? When I say non-negative, I mean greater than or equal to 0. So this is what I have to do. In order to find the domain, I need to solve the following inequality. 4 minus 3x is greater than or equal to 0. I'm not getting rid of the square root. I'm just saying that in order for this function to operate properly, the radicand, so whatever's under the square root, has to be greater than or equal to 0. So when we understand that, it'll make these problems very simple, right? Can we solve this inequality? How would we solve this inequality? All right, subtract 4 to the other side. So negative 3x is greater than or equal to negative 4. Now what? Very good. We need to remember this one rule. When dividing or multiplying both sides of an inequality by a negative number, it reverses the inequality. So it becomes x less than or equal to 4/3. Remember that. The inequality flips when multiplying or dividing by negatives. Remember that? So that's our domain. You can just say domain is from negative infinity to 4/3, including 4/3. Okay? So if you take any number from this set, you're guaranteed to get something positive under the square root. So the function produces a real answer. Is that okay? All right. Any questions on this? All right, let's try another one. Let's take a look at this function. X over x squared minus 9. So are there any issues that potentially can occur? Well, not holes, but like asymptotes. Things will go insane at those points, right? But you have to make sure that your denominator does not turn into 0. That's what you need to avoid here, because division by 0 is undefined. One thing you want to do is to factor. Then you see that 3 and negative 3 are both, yeah. So those are your vertical asymptotes, if you remember that from college algebra. So the function will start doing things like that. It will get, because again, the closer you get to 0, the larger the values you get for the ratio, right? If your denominator is close to 0, the quotients get infinite. So that's why that happens. It just flies asymptotically. That's a weird thing. But, so we just need to avoid positive and negative 3. So you have holes in the domain. Maybe that's what you were saying. So it's a number line with 2 holes in it. So one way to list that domain is everything from negative infinity to negative 3 union. Do you know what that is? It's basically gluing sets together from negative 3 to positive 3, union from 3 to infinity. So this is the entire number line with just 2 numbers removed, 3 and negative 3. Or it is much more convenient to express this using the set builder notation. The set is full of x's. What are those x's? Well, all x's except for 3 and negative 3. So it's much more condensed. Okay? So with the square roots, make sure the radicand stays non-negative. With quotients, make sure denominators don't turn into zeros. Well, the graph of this, we can do it really fast, actually. You have the asymptotes at negative 3, so something like that. You have an asymptote at positive 3. The horizontal one is 0, and we just judge that by the fact that the numerator is less than the denominator, degree of the numerator is less. So it will not, it will kind of get weird around the x-axis. You can cross the x-axis here, because that's the intercept, right? 0, when x equals 0, y equals 0, right? So all I need to do is just to test, because I have no idea where it's going to go. So I'm just going to say, how about y equals 1, x equals 1? What is the value if I plug in 1 in there? If I plug 1, the numerator is positive, the denominator is negative. So overall, negative, right? So then it's going to do this. And since that's a trick that I'm teaching in my college algebra, there's also multiplicity factor. Every multiplicity is 1, right? No, 1. I'm just looking at the powers, right? There are no exponents, so the multiplicity is 1. And we know from, maybe if you remember from college algebra, at odd multiplicities, the sign always changes at intercepts or asymptotes. So I'm just going to have to change the sign every time. So something like that. So it'll be the graph. I mean, it shouldn't turn like that. It approaches your asymptote. So the sign, that's the thing. You see how it's negative, positive, negative, positive, positive, negative. So the sign changes at all of those fun things. If I put a 2 in there, it will change this portion to that. That will be the only difference.
Wouldn't change the middle part?
Yeah, the x still remains odd. So you see negative 3 came from this parenthesis, has even multiplicity, so the sign will be positive from both ends. Yeah, it will get rid of the bottom portion, because it will cease to be a function. Yeah, so it will get rid of the bottom portion, but let me just go back to avoid the confusions in the notes. Here we go. You've done this in college algebra, right? The graphing of, I mean, we did it, graphing rational functions. It's not that big of a deal in pre-calc. I mean, if you don't know that, oh well. We'll reteach you that in Calc 1 properly. You know, go back graphing rational functions. Another one, f of x equals 2 over 1 minus 4x over x minus 3. Something like that. That's fun. You can. You might lose something out of your domain. Because remember, when we do the domain of the function, it's always the way the function appears. Because you can always manipulate your function to do something to it, but it's always the way it's written. So right away, there are two problems, right? Because you have two denominators. You have a denominator here, right? So that means 4x over x minus 3 has to work, right? Which means what? How do you make this work? Well, x minus 3 cannot be 0, right? So that means x cannot be 3. So the domain of this little fraction would be all x is such that x cannot equal to 3. So we have to make sure that that little fraction is happy. Because if you just multiply top and the bottom by x minus 3, you'll actually lose that x minus 3 factor. It might not, you might not be able to catch it later. See what I mean? But what else do we need to make sure? Yeah. we also need to make sure that 1 minus 4x over x minus 3 is not equal to 0, right? The whole denominator. So basically, let's just solve this equation. It's kind of weird, but let's just solve it for 0. Let's get rid of this. Just solve this, so you can do the x minus 3 now. Multiply both sides by x minus 3, x minus 3. This is x minus 3, by the way. So you'll get x minus 3, right, minus 4x equals 0. So what do we get? Negative 3x equals 3, right? So x equals negative 1. X cannot equal negative 1. So therefore, so the domain then of this entire function, in this case, we're actually taking the intersection of both sets. So x cannot equal negative 1, and x cannot equal positive 3. Right? So the domain here, x cannot equal negative 1, x cannot equal positive 3. So I had to take care of two things. Make the little fraction happen, then make the big fraction happen. Yeah, that's what you do. Now, don't write this down, but if I went ahead, what was the problem? It's 2 over 1 minus 4x over x minus 3. If I went ahead and just simplified this right away, multiply this by x minus 3 over x minus 3, see what happens. It's 2 times x minus 3 over x minus 3 when you multiply it this way, and then minus 4x. This is 2 times x minus 3 over negative 3x minus 3. So you're only catching the negative 1, but you're not catching the positive 3. If you simplify this, then it's really hard for you to know that x cannot equal positive 3.
Now, would you just like state those domain restrictions and then go to that?
No, you don't need to do that at all.
You're not?
No, no, no. I mean, if I ask you to do something else with that function, then yeah. But I'm just asking you for the domain. But I'm just showing you, if you start simplifying it, you have to be careful, because you might lose some of those points. Okay? So, but really, all it does, it kind of punches a hole in the graph. It's one of those removable discontinuities. Because all of a sudden, x equals 3 just gives you 0, right here. But over there, it gives you something that's undefined. So an example of something like that would be, take a look at this function, x squared minus 4 over x minus 2. Again, when we're asking you to find the domain, it's always relates to a function as it's written, without messing with it a lot. So what's the domain of this function as it's written? All real numbers except for 2. So the domain here is all real numbers except for 2. Although I can simplify this, right? It's very easy to simplify this function. It gives you x plus 2, x minus 2 over x minus 2. So x minus 2's cancel. And you're down to x plus 2. Doesn't feel like there is a problem with positive 2 anymore, but it's still not in the domain. The graph of this function is a straight line with a hole in it. Yeah, the graph of this function is the graph of x plus 2. It's x plus 2, the y-intercept is 2, the slope is 1. Only here, this point right here, the 2, 4 point is removed. There is a hole in it. So that's how you puncture a hole in a graph. Well, I don't know, you're making an experiment, something weird happened at 2. You know, I don't know, you have a monkey, you injecting monkey with tomato juice, At 2 pints, monkey explodes, but everything else is very linear. I don't know, something happens. So sometimes you have a phenomenon that's just very predictable, but at some point, just boom, an explosion. No asymptote, just nothing. So a lot of times, like if you have a parabola,
But if you end up simplifying that, still trying to use the original.
right? So the domain is always defined to the
It's plus 2, basically.
right. It's the x minus 2 in the denominator. If let's say I have this parabola, right? I have a parabola, let's say right here. So this is 2, 3 upside down parabola, right? Equation of this parabola is, let's say, x minus 2 squared plus 3, something like that. Okay, so if I simplify this, it's x squared minus 4x plus 4 plus 3, so it's x squared minus 4x plus 7, okay? But let's say, yeah, negative, sorry. Shit, I have to change everything. But you're right. Let me just erase it then. So it's negative, redo. So then it's negative x squared plus 4x minus 4 plus 3. So it's negative x squared plus 4x minus 1. Yeah, here we go. Good. But let's say I want to put a hole in it at 3. When x equals 3, you get a hole in the graph. Whatever happened, I don't know what happened. So the way you do that, you're just going to do this. You'll multiply it by x minus 3, and you'll divide it by x minus 3. So you're artificially putting that in the denominator, but also put it in the numerator, so it cancels. You still get the same parabola, but just the fact you have x minus 3 in the denominator creates a hole in there. So you can do this as a function like that, or you can just say, just x cannot equal 3. That's also okay. It just puts a hole in the graph. Something weird happened. I don't know. You lost the data point. You don't know what happens at that point. Everything else follows the parabola. At that point, you have no idea, so just, okay? How about this one? G of t equals 4 over 6 minus the square root of t plus 3. Finding the domain. Right, very good. So two things. You have to make the square root positive. So that means t plus 3 cannot be negative. So t plus 3 has to be greater than or equal to 0. Right? That's how you make square roots happy. By the way, if I change this to an 8th root, wouldn't change the way you make that happy. It will change the way you make the denominator happy, but the square root will stay kind of the same. So that's simple. T has to be greater than or equal to negative 3, right? So already for this entire function, you cannot consider t values that are less than 3, less than negative 3. Well, if it's equal to negative 3, you'll get 0, but you still have a 6, so it's 4 over 6. But you're right, if I didn't have that, if it was just 4 over the square root, you're exactly right, I would have to make it strictly positive, because you cannot have 0. But since I have that 6, that's not being affected by that square root, in that sense. 0, yeah. But also, 6 minus the square root of t plus 3 cannot be 0, right? The whole denominator cannot equal 0. Well, so basically we need to solve this equation, see when it does equal 0, and see what that gives us. So how do we solve equations like that? Yeah, separate. So that's equation involves radicals. First step is to isolate the radical. So move everything. Now what? Square everything, kill the radical. So square both sides. So that becomes 36 equals t plus 3. So then solve for t.
Would you do plus or minus 2 plus 2?
No, you're squaring. Squaring is just positive, right? If you were square rooting, then yes. T equals 33. Right? T can... Right, t has to be greater than or equal to negative 3, but not equal to 33. So there's a hole in there. Now, one thing that you need to remember, and that's what you learn in college algebra, or in 099, is that when you solve equations that involve radicals and you square both sides, sometimes you get those extraneous solutions. Sometimes you get a solution that doesn't work. So you really have to check. Not like with the denominators where you're like, well, all denominators are non-zero, so it works. Here you really have to check. If I take 33 and plug it in there, is that going to work? Yeah, right? So 33 plus 3 is 36, square 6, 6 minus 6 is 0. So that works. But, you know, you have to kind of check. The reason for it, don't write this down, and this is what I show to my students when I teach this technique. Here's a very simple equation, x equals 1. Wouldn't that be nice if all equations were like that? Solve this equation. What is the solution to this equation? 1, right? Is there anything else that solves this equation? No. But if for some whatever reason I decide to square both sides, x squared equals 1, what's the solution to this equation? That's where you need a plus or minus. So all of a sudden, x equals plus or minus 1. Negative 1 does not solve the original equation of x equals 1. So that would be the extraneous solution. So sometimes when you square both sides, you might end up with something that does not work in the original problem. Not the case here. So anyways, so t cannot equal 33. So I can say this. Oops. The domain is all real numbers such that x is greater than or equal to negative 3 and x cannot equal to 33. And it's totally fine that our variable is t and I'm using x to build this set, because it's just a set builder. I can call that variable anything I like. Or, in the interval notation, it is from negative 3, including negative 3, to 33, not including 33, union from 33. I just touched the board with myself from 33 to infinity. Those are two equivalent answers. Yeah, we never include infinity because you don't, just keeps going. Yeah. Okay. Is that clock is slow or fast? So it's a little tiny slow. I don't know. I wanted to talk to you. I'll do this on Friday. We don't have time to get into that. I want to get into the difference quotient thing. Remember that from algebra? The f of x plus h minus f of x over h. Difference quotient. We did that in algebra. All right. Well, we'll get into that because that's really important. So, but you can already start working on that My Math Lab homework. That's what you get, all those little videos and hints. And some of those problems, and let me show you, since we're still here, let me show you some of the questions. By the way, there's a lot of questions, 42 problems. I'm famous for that, but let's say here's question 1, and you'll see what I'm talking about. By the way, all of you might be getting different numbers when you do that. Determine whether the correspondence is a function. Yes or no? No, because e goes to 2 different values, right? So the answer is no. Final check? Fantastic. Done. Question 1 is complete. Question 2. Determine if the relation is a function. Domain each person in a family correspondence, each person's son. Range, a set of sons. So basically, can a person have more than one son? Yes, so therefore is that a function? Nope. Right, because you can have two sons. All right, nice work. Let's say you're confused. Help me solve this. It's exact same problem. Well, they just say, well, there's nothing to help. It's just you think about it a minute. View an example.
No, well, if you hit help me solve this, it brings up the
Exact same problem, and it guides you through that. But when you go back, it'll change the problem. So here it gives you a story of what's going on. Now, also, you see, like, when I'm working on question 2, it says it's 1.213. That's the problem out of the textbook. That's another way to see where the question comes from. 1.237. So it's section 1.2, question 37. And this is what I have here on our homework 2, if you just want to work straight out of the textbook. So you see, here's the question 37. So either way, what is this? There's like a, what is question 7? Oh yeah, look at this page. Give me question 7. That question 7? Oh yeah, there's animation. It's fun. Yeah, so it's all, it's good. And you get 42. Some of those, like I think, you won't be able to do all of it now, but you'll be able to get at least through, well, maybe halfway. After Friday, we'll do difference quotients, and then we'll do all the transformations. Basically, after Friday, you should be really all set, but you can start. And I mean, again, all of this is a review for you. You've done this all, so I don't know if you remember the definition of even-odd functions from college algebra. That's, again, my plan on Friday, but you can read up. I mean, you click on a textbook, it will actually literally pull up a chapter where it's from. Let me show you. But it will just start with the section, Here's a section on symmetry, read on about symmetry, and it will talk about odd and even function at some point, okay? So this is your book, by the way. See how cool it is? It will just open up a book. Oh, here we go. Here's some fun things. Remember I was looking for the clickies? Here's a clicky. Little video right in the book. There's a little lady going to talk about some stuff. Look at this. You don't need me.
My brother's in Steve Craig's math class, so he's doing a lot of YouTube stuff, and it's so weird just being at home.
Yeah.
Steve Craig's like talking in the background.
This is what I'm doing here with all my, last semester we had fun. I was double booking. I had an online class, and I just told my online students to log in live, and I just broadcasted my regular lectures, and they had to log in, and they were just like, it actually kind of worked, because in the summer, I taught 2 online